In 1774, an entire street in Paris disappeared into the ground. Houses, carts, and cobblestones descended 84 feet into darkness. Below the city, workers had been carving tunnels for 1,000 years. By the 18th century, Paris sat above 350 kilometers of empty quarries. The city was collapsing into itself. Engineers faced a question: how do you prevent an entire capital from sinking underground? And then they had to decide what to do with 6 million bodies from overflowing cemeteries. Tonight, we examine how they solved both problems with the same network of tunnels. Welcome to Midnight Engineer. This channel explores engineering history in detail. The content is designed for sleep and relaxation. Each video presents technical information in a calm, methodical format. Tonight's episode examines underground engineering projects across history. If you enjoy detailed engineering stories, consider subscribing to the channel. New videos are released each week. Now, let's begin tonight's topic. The Paris Catacombs system extends beneath the city for approximately 350 kilometers. The tunnels originated as limestone quarries during the Gallo-Roman period. Workers extracted Lutetia limestone from these underground chambers to construct buildings above ground. The quarrying operations continued from Roman times through the 18th century. By 1774, structural problems emerged. A sinkhole on Rue de l'Enfer measured 84 feet in depth. Houses and carts descended into the collapsed ground. King Louis XVI established the Inspection Générale des Carrières in 1777 to address these failures. Inspector Charles-Axel Guillaumot began mapping the abandoned quarries. The underground network measured approximately 800 hectares in total area. Limestone extraction began in the 1st century during Roman occupation. The city known as Lutetia required building materials. Workers identified deposits of high-quality limestone in areas south of the Seine River. Open-pit mining characterized the initial extraction methods. As surface deposits depleted, miners moved underground. Tunnels followed the limestone seams horizontally. Support pillars remained to hold the ceiling. Each pillar measured approximately 2 meters square. The spacing between pillars varied from 3 to 6 meters. Over centuries, the tunnel network expanded without central planning or mapping. By the Middle Ages, multiple independent quarrying operations existed. Individual landowners controlled extraction on their properties. No authority coordinated the underground activities. Tunnels intersected at random angles. Some areas featured double or triple layers of excavation. The deepest workings reached 30 meters below street level. Workers used hand tools, including picks and chisels. Iron wedges split the limestone along natural fracture lines. Each block weighed between 50 and 200 kilograms. Transportation occurred via human carriers or small carts. Rope and pulley systems lifted blocks to the surface. The quarries provided material for notable structures. Notre Dame Cathedral used Lutetia limestone extensively. The Louvre Palace incorporated blocks from southern quarries. City walls constructed during various periods required massive quantities. Private residences of wealthy citizens featured limestone facades. By the 17th century, Paris had grown substantially. Construction above ground accelerated. The demand for limestone increased correspondingly. Quarrying expanded beneath newly populated areas. The relationship between surface and subsurface became dangerously disconnected. The first documented major collapse occurred on April 17, 1774. Rue de l'Enfer, meaning Hell Street, experienced catastrophic failure. A section measuring approximately 300 meters in length collapsed. The depth of the resulting crater reached 25 to 30 meters. Several buildings fell into the void. Eyewitnesses described a tremendous noise preceding the collapse. The ground first showed cracks that widened over several hours. Residents evacuated before the main failure. No fatalities occurred in this particular incident. However, the event created widespread alarm throughout the city. Investigation revealed the cause. Quarry ceilings had deteriorated over centuries. Water infiltration weakened the limestone. Support pillars eroded from the base. The weight of overlying buildings exceeded design margins. No formal calculation had ever determined safe loading. The medieval quarrymen worked by experience and intuition. Modern buildings concentrated loads differently than earlier structures. Streets paved with stone added significant weight. Underground water flow patterns had changed. Springs and wells altered the moisture content of rock formations. King Louis XVI responded by decree on April 4, 1777. The Inspection Générale des Carrières received official status. Charles-Axel Guillaumot served as chief inspector. His salary amounted to 6,000 livres annually. A staff of surveyors, engineers, and workers assisted him. Their primary mission involved mapping existing quarries. The secondary objective required stabilization of dangerous areas. The work would consume decades. Guillaumot recognized the magnitude immediately. The surveying process began systematically. Teams entered known quarry entrances. They carried measuring chains, plumb bobs, and compasses. Lanterns provided illumination in the darkness. Each tunnel section received measurement and documentation. The height and width varied considerably. Some passages allowed upright walking, others required crawling. Dead ends appeared frequently. Collapsed sections blocked many routes. Water filled lower elevations. The surveyors noted everything on detailed plans. Vertical shafts connected different levels. These measured 1 to 2 meters in diameter. Depths ranged from 10 to 30 meters. Some shafts had crumbled and become impassable. Others retained wooden or stone linings. The surveyors lowered measuring lines to determine exact depths. They correlated underground findings with surface locations. Street names and building positions appeared on the maps. Property boundaries overlay the tunnel networks. The resulting documents showed the relationship clearly. Guillaumot implemented a standardization system. Each tunnel section received identification marks. Roman numerals carved into walls indicated primary passages. Arabic numbers designated secondary routes. Letters marked individual chambers or rooms. The system allowed navigation through the complex maze. Workers painted these marks using lime-based pigment. The white markings remained visible for centuries. Modern visitors still observe the original numbering system. The complete mapping required 15 years of continuous effort. By 1792, surveyors had documented most accessible areas. The total measured length exceeded 280 kilometers of passages. An estimated additional 70 kilometers remained unmapped. These sections had collapsed or flooded completely. The maps filled numerous large format sheets. Guillaumot stored them at inspection headquarters. Copies went to relevant government offices. The documentation revealed the extent of the underground city. Simultaneously, Paris faced a public health crisis above ground. Cemetery overcrowding had reached critical levels. The Cimetière des Innocents represented the most severe case. Located near Les Halles Market, it operated for over 600 years. Approximately 2 million bodies occupied the site. The area measured only 6,000 square meters. Mass graves held 1,500 bodies each. Workers kept graves open during the filling process. This lasted several months per grave. Decomposition occurred slowly in the densely packed earth. The cemetery walls bordered residential properties. Residents reported overwhelming odors. Decomposition gases seeped into neighboring cellars. In 1780, a basement wall collapsed under the weight of remains. Human bones and soil spilled into the property. The owner complained to authorities. Inspection confirmed structural failure caused by mass grave pressure. The incident forced immediate action. The city council declared the cemetery closed. All within-city burials received prohibition after 1780. The closure created a new problem. Paris required disposal space for approximately 3,000 deaths monthly. Suburban cemeteries could not absorb this volume. Transportation of bodies across the city raised concerns. Summer heat accelerated decomposition during transit. The logistics appeared impossible. Officials considered various solutions. Expanding suburban cemeteries required land acquisition. Creating entirely new facilities needed substantial investment. The timeline for either option stretched across years. Guillaumot proposed an innovative approach. The mapped quarries offered ready-made underground storage. The empty spaces could accommodate millions of remains. The location sat outside city limits at that time. The depth provided natural isolation. Temperature remained constant year-round. Humidity levels stayed moderate. The limestone walls required no modification. Access existed via multiple entrances. The solution addressed both problems simultaneously. The city council approved the plan in 1785. The site received consecration on April 7, 1786. The location took the name Paris Municipal Ossuary. Later, it became known as the Catacombs. This referenced the Roman catacombs discovered earlier. The reference held mostly symbolic meaning. The Roman catacombs served different religious purposes. The Paris version functioned as organized storage. Preparation work began immediately. Workers reinforced unstable sections. They constructed retaining walls using limestone blocks. Floor levels received grading for drainage. Stairs provided access from the surface. The main entrance shaft measured 4 meters in diameter. It descended 20 meters vertically. At the bottom, horizontal passages extended in multiple directions. Storage chambers opened off these main corridors. The transfer of remains began in December 1785. Work occurred exclusively at night. This avoided public disturbance and religious objections. Black cloth covered wagons transporting bones. Priests accompanied each convoy. The route followed designated streets. Guards prevented unauthorized observation. The procession moved slowly through the city. Upon arrival, workers unloaded into the vertical shaft. Baskets lowered bones to the tunnel level. Underground workers received and stacked the remains. Additional cemeteries followed. Saint-Étienne-des-Grès closed in 1787. This cemetery dated from medieval times. The remains reflected several centuries of burials. Notre-Dame des Blancs-Manteaux contributed next. Then came Madeleine Cemetery. The Revolutionary period added more sources. The Arancis Cemetery held victims of the guillotine. These remains transferred during the 1790s. By 1788, transfers continued regularly. The pace occasionally slowed due to political upheaval. The French Revolution disrupted many government operations. Operations resumed under Napoleon. Additional cemetery closures occurred during the 19th century. Baron Haussmann's reconstruction of Paris eliminated many churchyards. These remains went to the catacombs. The final major transfer happened in 1860. By then, 6 million remains occupied the tunnels. This represented approximately 3 times the living population of Paris. The initial deposits showed no particular organization. Workers simply stacked bones in available spaces. The result resembled a warehouse more than a memorial. In 1810, Louis-Étienne Héricard de Thury became director. He implemented significant changes. The goal involved creating a visitable mausoleum. The bones required artistic arrangement. Thury designed geometric patterns using skulls and long bones. Workers dismantled existing stacks and rebuilt them. The new arrangements followed consistent patterns. Bones formed walls approximately 2 meters high. Tibias and femurs created the main structure. Skulls punctuated the walls at regular intervals. Some designs incorporated crosses. Others featured heart shapes. Decorative borders appeared between sections. The visual effects suggested deliberate memorial design. Touré added stone tablets with inscriptions. These contained quotes about mortality. French and Latin text appeared. The passages quoted religious and philosophical sources. Architectural elements enhanced the space. Stone archways marked important intersections. These bore carved inscriptions identifying cemetery sources. One arch read, "Arrête, c'est ici l'empire de la mort," meaning, "Stop, this is the empire of death." Another stated the ossuary's consecration date. Touré installed plaques describing specific remains. These identified notable individuals when possible. Most remains remained anonymous. The sheer numbers prevented individual identification. A small museum area displayed unusual finds. Skeletal deformities appeared in glass cases. These illustrated various medical conditions. Mineral samples from the quarries occupied another section. Touré catalogued local geology. The displays served educational purposes. They explained the underground environment. Visitors could understand the natural history alongside human history. The catacombs opened to public visits by appointment in 1809. Interest proved immediate and substantial. Visitors included French citizens and foreign tourists. Napoleon III descended into the tunnels in 1860. He brought his son on the tour. Many European nobility visited. The attraction combined morbid curiosity with architectural interest. The orderly bone arrangements impressed visitors. The scale seemed incomprehensible. 6 million remains exceeded easy visualization. Public access expanded gradually. By 1874, regular visiting hours existed. No appointment requirement remained. Tickets went on sale at the entrance. The route covered approximately 1.5 kilometers. This represented less than 1% of total tunnel length. The tour required 45 minutes at normal walking pace. Stairs descended 131 steps at the entrance. The exit required climbing 112 steps. The temperature remained constant at 14 degrees Celsius. Humidity stayed at approximately 80%. During World War II, the tunnels served resistance fighters. Colonel Roltanguy established headquarters in a hidden chamber. The location allowed secure communications. German forces never discovered it. The resistance coordinated Paris liberation efforts from this spot. Meanwhile, the Wehrmacht built a bunker beneath Lycée Montaigne. This German installation occupied a different tunnel section. The two sides unknowingly worked nearby. Neither detected the other's presence. Illegal exploration became common in modern times. These explorers call themselves cataphiles. They accessed the closed sections through secret entrances. The police established a special unit called cataflics. These officers patrol the tunnels. They seal unauthorized openings. Cataphiles create maps of restricted areas. Some sections contain artwork or installations. Underground parties occasionally occur. The activity remains illegal despite its popularity. In 2004, police discovered a fully equipped movie theater. This included a screen, projector, and seats. A bar and restaurant area adjoined the theater. The creator's identity remained unknown. Current management involves multiple agencies. Paris Musées oversees the tourist section. The Inspection Générale des Carrières maintains structural integrity. Approximately 550,000 visitors tour annually. This makes the catacombs among Paris's most popular attractions. The site has UNESCO World Heritage consideration. The combination of engineering and history justifies this status. The catacombs represent a unique solution to dual urban problems. This completes our exploration of Paris's underground engineering. The catacombs solved two problems with one innovative solution. Now, we turn our attention to another city facing an underground crisis. In the mid-19th century, London confronted a sanitation emergency that threatened the entire population. The solution would require engineering on an even larger scale. London's sewer system extends approximately 1,300 miles beneath the city. The main interceptor sewers measure 82 miles in combined length. Joseph Bazalgette designed and constructed the system between 1859 and 1875. The project required 318 million bricks. Workers excavated 2.7 million cubic meters of earth. The construction consumed 670,000 cubic meters of concrete. 4 major pumping stations lifted sewage from low-lying areas. The system eliminated cholera epidemics from London. It remains functional today, serving modern Greater London. The design capacity exceeded original requirements by significant margins. This foresight allowed for population growth over 150 years. Before Bazalgette's intervention, London faced catastrophic sanitary conditions. The River Thames functioned as an open sewer. Raw sewage emptied directly into the river. Industrial waste joined human waste. Slaughterhouse effluent added to the pollution. Dead animals floated in the water. The river contained no fish. Other wildlife avoided the toxic environment. The Thames flowed slowly through central London. Tides pushed sewage upstream and downstream. The waste never reached the sea. It accumulated in the river mud. Cesspits served most buildings. These underground tanks collected waste. Workers called nightmen emptied them periodically. They worked after dark to minimize public offense. The contents went to farmers as fertilizer. The system worked adequately in earlier centuries. London's population growth overwhelmed the capacity. By 1800, 1 million people lived in the city. By 1850, the number reached 2.5 million. Cesspit capacity remained unchanged. Many property owners neglected maintenance. Full cesspits leaked into surrounding soil. The introduction of flush toilets worsened conditions. These devices used substantial water volumes. The water overwhelmed existing cesspits. The liquid contents overflowed into streets. Some flowed through cracks into basements. An 1847 law required cesspits to connect to sewers. The existing sewers had served as street drainage. They directed rainwater to the Thames. Adding sewage filled them beyond capacity. The overflow entered the river at hundreds of locations. The policy aimed to eliminate cesspits. It successfully created a far worse problem. Disease resulted inevitably from the conditions. Cholera appeared in London in 1831. This bacterium thrives in contaminated water. The disease causes severe dehydration. Without treatment, death occurs within days. The first epidemic killed 6,000 people. A second outbreak in 1848 killed 14,137 residents. Another epidemic struck in 1854, causing 10,738 deaths. The 1866 cholera outbreak killed 5,596 people. Each epidemic terrified the population. No one understood the cause. Medical theory blamed miasma, or bad air. The smell seemed to prove this theory. Dr. John Snow challenged the miasma theory. He investigated the 1854 outbreak in Soho. The cases clustered near Broad Street. Snow mapped each death's location. The pattern centered on a public water pump. He examined the pump water. It appeared clear and fresh. Chemical analysis showed no obvious contamination. Snow theorized invisible pollution existed. He persuaded authorities to remove the pump handle. New cases stopped immediately. This suggested water transmission. Snow's evidence proved correct. The medical establishment ignored him. They continued believing in miasma transmission. The summer of 1858 forced government action. June temperatures exceeded normal ranges. The Thames reached unprecedented pollution levels. Heat accelerated decomposition of sewage. Hydrogen sulfide and methane gases released continuously. The smell became unbearable across central London. Parliament sat in session at Westminster. The building directly overlooked the Thames. Members of Parliament could not endure the odor. They hung sheets soaked in lime chloride over windows. The treatment provided minimal relief. Parliament considered relocating to Oxford or another city. Benjamin Disraeli, then Chancellor of the Exchequer, seized the opportunity. He argued for immediate sewer construction. The crisis made objections impossible. Parliament passed an Enabling Act on August 2, 1858. This provided £3 million funding initially. The amount later doubled. The final cost reached £6.5 million. This represented £650 million in modern currency. The Metropolitan Board of Works received responsibility. They appointed Joseph Bazalgette as chief engineer. Joseph William Bazalgette was born March 28, 1819. His family descended from French Huguenots. He trained as a civil engineer under Sir John McNeill. His early work involved railway projects. He worked in China and Ireland, gaining experience. By 1842, he established a London consulting practice. The work proved demanding. In 1847, he suffered a nervous breakdown. He spent a year recovering in the countryside. In 1849, the Metropolitan Commission of Sewers appointed him assistant surveyor. His salary amounted to £250 annually. The commission's previous engineer died of work-related stress. Bazalgette assumed increasing responsibility. In 1852, he became chief engineer. The Metropolitan Board of Works replaced the commission in 1856. Bazalgette continued as chief engineer. His salary increased to £1,000 annually. He would hold this position for 33 years. Bazalgette had spent years developing sewer plans. Previous proposals gained no political support. The costs seemed excessive. Multiple authorities disagreed on approaches. The Great Stink changed everything. Suddenly, Bazalgette's plans received approval. He could finally implement his vision. Bazalgette's system used gravity to move sewage eastward. The Thames flows from west to east through London. Sewage needed to bypass central London entirely. Pumping stations would lift waste where necessary. Otherwise, gravity provided the motive force. The system required minimal operating costs. This feature proved essential for long-term sustainability. 6 main interceptor sewers formed the backbone. 3 served areas north of the Thames. 3 covered southern districts. The northern high-level sewer ran along elevated ground. This collected waste from areas like Hampstead. The northern mid-level sewer served districts at intermediate elevation. The northern low-level sewer ran along the Thames embankment. These 3 sewers converged at Abbey Mills pumping station. The southern sewers mirrored the northern arrangement. The southern high-level sewer collected from elevated southern districts. The southern mid-level and low-level sewers served progressively lower areas. These converged at Deptford and Crossness pumping stations. From the pumping stations, outfall sewers carried waste to the Thames estuary. The discharge points sat far east of populated areas. The tide carried sewage out to sea. The interceptor sewers measured between 2 and 3 meters in diameter. The largest reached 3.65 meters. Cross-sections took oval or egg-shaped profiles. This shape moved sediment effectively during low flows. The slope gradient varied by location. Typically, it measured between 1 in 1,000 and 1 in 3,000. This provided adequate flow without excessive erosion. The sewers used Portland cement for water resistance. This cement type hardens when exposed to water. The resulting material lasts indefinitely. Smaller local sewers fed the interceptor sewers. These totaled 450 miles in length. They collected from individual buildings and streets. The local sewers typically measured between 0.5 and 1 meter in diameter. Some incorporated London's lost rivers. The River Fleet flowed beneath Fleet Street. This natural watercourse became part of the system. Similar integration occurred with other streams. Construction commenced in 1859. The work occurred in multiple locations simultaneously. Bazalgette divided London into administrative sections. Each section had assigned crews and supervisors. The Metropolitan Board of Works employed thousands of workers. Additional contractors provided specialized services. The construction method involved open trenches. Workers excavated from the surface down to required depths. The trenches measured 3 to 6 meters wide. Depth varied from 3 to 7 meters. Wooden supports prevented collapse. Workers removed earth using shovels and wheelbarrows. Horse-drawn carts transported spoil to disposal sites. The volume of excavated material exceeded 9 million cubic meters. Much of this filled marshy areas or created new parkland. Bricklaying proceeded as excavation completed each section. Specialized bricklayers worked rapidly. Each brick required mortar application and careful placement. The walls needed complete watertightness. Any gaps would leak sewage into surrounding soil. Quality control proved essential. Bazalgette personally inspected much work. Surviving documents show thousands of his handwritten comments. These include approved JWB on acceptable sections. Others note required corrections or improvements. The egg-shaped sewers required temporary wooden forms. Carpenters built these to exact specifications. Bricklayers constructed the walls against the forms. After mortar cured, workers removed the forms. The process moved to the next section. Each 100-meter section required several weeks. Multiple crews worked different sections simultaneously. The coordination challenge demanded careful management. The Thames embankment provided additional complexity. This project combined multiple functions. The embankment reclaimed land from the Thames. New roadways provided traffic relief. The Victoria embankment created public gardens. Underground, the low-level sewer ran through special chambers. The district line of the London Underground also occupied embankment space. 3 separate construction projects proceeded simultaneously. Coordination prevented conflicts and delays. The Victoria embankment officially opened July 13, 1870. 4 major pumping stations provided critical functionality. These lifted sewage from low-lying sewers to higher outfall pipes. The stations combined engineering necessity with architectural grandeur. Victorian designers believed public infrastructure deserved aesthetic quality. Abbey Mills Pumping Station served northern sewers. Located in East London, it featured ornate design. The building resembled a Byzantine cathedral. Colorful brickwork created geometric patterns. Tall windows admitted natural light. Inside, massive beam engines dominated the space. These engines measured over 10 meters tall. They weighed 55 tons each. 4 engines operated initially. Each produced 148 horsepower. The engine's rhythmic motion was visible and audible. The machinery's precision impressed visitors. Steam powered the engines using coal-fired boilers. Crossness Pumping Station served southern sewers. Located on the Erith marshes, it matched Abbey Mills in grandeur. The architect chose Romanesque style. Red and yellow brickwork created striking contrast. Inside, 4 beam engines performed the lifting work. Prince Consort, Victoria, Albert Edward, and Alexandra were their names. These honored the royal family. Each engine could pump 6,000 gallons per stroke. The stroke rate reached 6 per minute. This meant 36,000 gallons per minute per engine. The total capacity reached 144,000 gallons per minute from all 4 engines combined. The engine house featured spectacular ironwork. Cast iron columns supported the roof. These contained decorative elements painted in bright colors. Gold leaf highlighted important details. The floor used decorative tiles arranged in patterns. The overall effect suggested a palace rather than a sewage facility. Prince Edward, the future King Edward VII, officially opened the station April 4, 1865. Deptford Pumping Station handled additional southern flow. The design prioritized function over decoration. The building appeared more industrial. However, it still featured quality construction and materials. Western Pumping Station completed the set. This handled flows from western districts. Together, the 4 stations ensured the entire system functioned correctly. The main construction concluded by 1875. Some sections opened earlier as construction completed. The northern low-level sewer became operational in 1868. The southern system followed in 1869. Remaining sections came online between 1870 and 1875. Total construction time spanned 16 years. The project employed approximately 5,000 workers at peak periods. Construction accidents killed relatively few workers considering the scale. Precise fatality numbers remain unclear. Historical records suggest fewer than 100 deaths occurred. The impact on public health appeared immediately. Cholera cases dropped dramatically. The 1866 epidemic was the last significant outbreak. This occurred before system completion. Areas still using old drainage experienced infections. Completed sections showed 0 cases. This provided final proof of waterborne transmission. The miasma theory lost all credibility. Typhoid cases also declined substantially. Other waterborne diseases became rare. London's death rate decreased significantly. Life expectancy increased. The sewer system's public health benefit exceeded all expectations. The Thames water quality improved noticeably. Fish returned to the river by 1900. The first salmon appeared in 1974. Wildlife populations recovered gradually. The riverbanks lost their toxic character. Properties along the Thames gained value. The river became an asset rather than liability. Bazalgette's achievement transformed London permanently. Bazalgette introduced several innovations. The use of Portland cement represented one advancement. Previous sewers used brick with lime mortar. This gradually deteriorated. Portland cement resisted water indefinitely. The material required specific mixing ratios. Quality control ensured consistency. The resulting sewers remained solid 150 years later. The egg-shaped cross-section improved flow characteristics. Traditional circular pipes accumulated sediment at low flow. The pointed bottom concentrated flow. This created scouring action. Sediment moved continuously toward treatment facilities. The design required no manual cleaning under normal conditions. Bazalgette deliberately oversized the sewers. His calculations showed required diameters. He doubled these measurements. This decision proved brilliant. London's population grew far beyond Victorian projections. The oversized sewers handled increased flow. The system avoided obsolescence for over a century. Modern London still relies on Bazalgette's infrastructure. The interceptor concept itself represented innovation. Earlier proposals suggested smaller, local improvements. Bazalgette recognized the need for comprehensive approach. Individual districts could not solve citywide problems. The interceptor sewers captured waste before it reached the Thames. This required coordination across all districts. The Metropolitan Board of Works provided necessary authority. Bazalgette implemented unified design standards. This ensured compatibility and efficiency. Joseph Bazalgette received knighthood in 1875. Queen Victoria recognized his achievement. Professional societies elected him to leadership. The Institution of Civil Engineers made him president in 1883. He continued working until 1889. The London County Council replaced the Metropolitan Board of Works that year. Bazalgette retired at age 70. He died March 15, 1891. He was buried at St. Mary's Church, Wimbledon. Bazalgette's sewers remain operational today. Modern London generates far more sewage than Victorian London. The system still handles the load. Some sections require repair or replacement. The basic infrastructure continues functioning. Engineers consider this remarkable longevity. Few 19th century systems remain in daily use. Bazalgette's achievement stands among history's greatest civil engineering projects. This completes our exploration. If you liked my video and my content, please like, comment, and subscribe to my channel.